to use this noise. There it is. Perfect. Yeah, there's a nice. There, got it. All right. Okay. All right. Yeah. Ready to start off the seminar?
Yeah. All right. Good afternoon, everyone. We'll begin today's RSES seminar by paying respect to the people that we are meeting on. So for Canberra, it's the land of the Ngunnawal and Ngambri people, and we acknowledge our elders and we pay respect to the elders, past, present, and emerging. So very happy to have our own Caroline be speaking to us, which Harold will introduce a bit more about her in a bit. And just to, probably some of you have seen the RSES or email, our microphone is missing. No questions asked if you're the one that take it. And that also means we cannot have questions asked online today. So if you have any questions from the people online, feel in to type in chat. And if there's anything that we need to adjust for AV, also send a direct message to me on the Zoom chat. So without further ado, everybody.
Hello, everyone. It's nice to see so many of you today before the long weekend. And it's my great pleasure to introduce today's speaker, Caroline Eakin, who obtained her Master of Science in Geophysics degree from the Imperial College London, the Royal School of Mines, in 2010 with the Watts pedal. During that time, she spent a year abroad in the United States at the University of California, Berkeley. Then, from 2010 to 2014, she was working towards her PhD at Yale University, where she got the Loomis Prize. She graduated in 2014, the end of 2014, and then from 2015, she was a postdoc at Southampton University until mid-2016, where we were lucky to receive her application, and she started her continuing position here at RSES, so mid-2016. In the meantime, she was promoted, and she's a fellow today. So in her young research career, Caroline achieved outstanding results that goes back to her undergraduate student days when she worked on the Cascadia subduction zone. And then, apart from these results, she published a series of influential papers on the Cascadia subduction zone. And that was followed by the work on the South American subduction zone, in particular on the Peruvian flat type of subduction, where she also achieved outstanding results. That was followed by the work on the Nazca Plate and work on the Amazon Basin. Again, outstanding results, a series of influential papers. And from there, she sort of, among other topics, she started working on the Australian continent. And this is something that you will hear today. And I'm very happy to be on the same team with Caroline on our work on the Macquarie Ridge complex. And hopefully some outstanding results will come from that project too. So, yeah, fingers crossed. So in her everyday's work, Caroline is using seismology as the main tool. But in particular, anisotropy. So for non-seismologists among you, anisotropy is simply a property of the medium to behave differently in the different directions. And in this context, the speed of seismic waves will behave differently in different directions. So instead of just measuring the travel time and speed of seismic waves, you look at how they vary in space. And it turns out that from there, you can tell something about the property of the medium through which the waves propagate. But you can also tell something about the evolution and the past of that same material. But apart from just working in front of a computer, Caroline goes to the field. And one of my favorite stories is that when we went to the Furious 50s in 2020, you know, the place where you really have to have a stomach for the formidable conditions of the Southern Ocean. While all of us were going home to take some rest after that voyage, she jumped on the plane and went to the Lake Erie Basin in South Australia, where she serviced the experiment that she set there with the helicopter. So some extreme geophysics for sure. So last but not least, Caroline has received already many awards, most notably the Australian Research Council DECRA, which is expiring this year. But most recently, she has been awarded the Outstanding Early Career Scientist Award by the European Geosciences Union. So for all of these reasons, we are extremely lucky to have Caroline here. And it's with a great pleasure I introduce her as today's speaker. Thank you.
Thank you very much, Hrvoje, for that very kind introduction. And thank you everyone for being here. I wasn't expecting so many people right before the long weekend, but this is great. So I guess to start off, as Hrvoje mentioned, actually, after that trip on to Macquarie on the ship, and I went to participate in fieldwork around Lake Eyre, and I went in a helicopter above the Simpson Desert. And this is actually a picture from that trip from the helicopter of the Simpson Desert. And the reason I'm showing it really is just a picture to express the Australian red centre. So Australia is this vast continent, it's flat, and it's mostly covered in a blanket of thin sediments or regolith. But beneath that veneer lies a rich tectonic history. And it's that tectonic history that I'm interested in, and to explore beneath these sediments using seismology to really ask the question, how deep is that tectonic signature expressed in the Australian continent at depth in the mantle? So this rich tectonic history is most well seen in terms of, if you just look at a geological map, so the surface geology, or here showing the major geological provinces of Australia. And the sort of basic geology of the continent is that the western 2/3 are older and the eastern part of Australia is younger. So the colors here represent the age. The Archean cratons, the Yilgarn and the Pilbara in Western Australia are Archean. We've also got the Gawler craton in South Australia, which is between Archean and Proterozoic. And then the pink colors are other Proterozoic elements. So we're talking kind of Precambrian. So we're talking billions of years old, part of the Australian continent.
Sorry, the slides are not progressing. Quite unusual.
Yeah,
It's just a bit not to steal the thunder. Sorry about that.
Is it coming up on yours?
This is annoying. Sorry about that.
Sorry, everyone.
But then again, that jinx has started when the microphone is missing, but we're gonna retry this whole thing. Just gonna share screen first. Where's the mouse? I can't.
How does it feel, Caroline?
You're the one with the jokes.
All right, perfect. Sorry, keep going.
All right, thank you. Right, where were we? Okay, so the western 2/3 is older, Precambrian, and then in Phanerozoic, we have Eastern Australia being, we had subduction along the east coast of Australia, accreting these terrains onto Australia. Nope.
I was just gonna.
It's looking okay.
It's looking all right. Okay, sorry about that.
At least it's only me, right? It's fine. We're all friends. Right. So since 90 million years ago, in the breakup of Eastern Gondwana, the Australian continent separated from Antarctica and Zealandia to form the present-day passive continental margins. And since then, the Australian continent has been moving rapidly northwards, today colliding with Southeast Asia. And today, the Australian continent is the fastest moving continent on Earth, moving rapidly northwards. And that rapid motion of the Australian continent, as it's moving above the mantle, is expected to exert significant shear on the underlying mantle or asthenosphere below. So this tectonic history of Australia, expressed in the surface geology, controls many things. Perhaps obviously exerts a first order control on the mineral distribution in Australia, which is important for Australia's economy. As a seismologist, it's interesting to note that it also exerts a control over the distribution of intraplate seismicity in Australia. Australia does get earthquakes, about 100 magnitude 3 earthquakes every year, but they're not uniformly distributed across the continent. They occur in certain regions, and those regions are particular weak zones, often past suture zones or past tectonic boundaries, which are weak and then focus the seismic deformation. So this geological history and this geology of the surface is well characterized in the Australian crust by looking at different geophysical techniques. So on the top left, we've got the gravity, magnetics, radiometric, so concentration of elements like thorium, potassium, uranium. And on the bottom right, we've got the seismic Moho, so the boundary between the crust and the mantle. This is from a compilation from Brian's book. He's got some of the geological boundaries on top, and you can see a correspondence between these different geophysical characterizations and what we already know about where the major geological provinces are and their boundaries. And some of this information is used to actually define those boundaries and those outlines. If we go deeper, however, and look at images of the Australian lithosphere, then it becomes much more difficult to make a comparison and really try to make connections between the geology and the lithosphere. Even though when we built the Australian continent, we assembled different pieces of crust, we also must have assembled different pieces of lithosphere. But it's much harder to get the same resolution at deeper depths with geophysical methods. So here we're looking at different cross sections of seismic tomography at different depths. So from 100 kilometers up on the top left, 150, 200. The colors represent seismic wave speed, particularly the speed of vertically polarized shear waves, where we've got green colors. They represent seismic waves traveling faster through the lithosphere, so through material which is colder and stronger. And where we've got the warmer brown colors, that represents slower seismic velocities, and that's representing in these cross sections that we're in the asthenosphere. We're in warmer, weaker material. So when we're at 100 kilometers depth, we can see that for Eastern Australia, we're already into the asthenosphere. We think that the lithosphere is quite thin beneath Eastern Australia, probably around 70 to 75 kilometers thick. But we can see that for most of the Central and Western Australia, 2/3 of the continent, we do see the lithosphere in green, and we can see that extending down to 200 kilometers, and it probably in seismic tomography, the lithosphere extends down maybe 250, 300 kilometers depth even. And whilst we might be able to pick out certain regions, maybe in Western and Central Australia, where the velocities are particularly fast and the lithosphere might be a bit deeper, it would be really difficult to take these images and see a detailed correspondence with the geological boundaries or the surface geology like we could do for the crust. So what I'm interested in, and what I think is helpful for looking at the lithosphere, is something called seismic anisotropy. And Hervoy already gave a great introduction as to what seismic anisotropy is. But to say again, anisotropy, that word, means directional dependence of any kind of physical property. But when we're talking about seismic anisotropy, we're talking about a directional dependence in seismic velocity or seismic wave speed. And what's really cool is that the mineral olivine, which is the primary constituent of the upper mantle, olivine crystals are anisotropic. So when waves travel in different directions through an olivine crystal, as shown in the figure, and the numbers, they travel at different seismic velocities. And there's a particular axis, the A-axis, which is the fastest direction of travel for seismic waves. And what's really useful is when the upper mantle undergoes deformation, so that might be from shear of the mantle, convective flow in the upper mantle. Under typical upper mantle conditions, the olivine crystals and the fast axis of the olivine crystals in particular will tend to align with the mantle flow or the shear direction of that deformation. So this is a really useful property for then, as seismologists, to actually try and observe, actually make a direct observation or inference of the mantle flow field from seismic observations. So in this cartoon shown, if you imagine that we have a tectonic plate and it's moving over the surface of the Earth and it's exerting a drag on the asthenosphere below. So you can think of that having a tub or a bathtub of water and you're sort of dragging your hand along the top of it. That then sort of drag or shear then gets expressed in the deformation. It rotates the olivine crystals into a preferred orientation with all the fast axes aligned. And we tend to see, for the upper mantle, tend to expect to see the fast direction aligned with the plate motion. For the lithosphere, however, anisotropy can be frozen into the lithosphere, representing the time that it was last deformed, so the last major deformational event. So it doesn't look like the plate motion today because the lithosphere in general is strong and rigid, but it can be deformed, for example, at plate boundaries when it's being formed at a mid-ocean ridge and spreading away, or for example, at a past orogeny or mountain building event. And there's evidence that that lithosphere will freeze in or fossilize the anisotropy from that last episode of deformation. It's a bit like at a mid-ocean ridge when you're creating new crust and you freeze in the magnetic field as that crust is cooling. It's the same thing with the lithosphere. You can kind of freeze in the anisotropy from the time of that deformation. Okay, so what do we already know about the anisotropy of the Australian continent and below? So the two images here on the right show different depth slices, 100 and 200 kilometers, for a surface wave model looking at azimuthal anisotropy. So all the black bars represent, you can think of that as the fast direction. And where the bars are longer, the anisotropy is stronger, and the direction represents the fast direction, as I said. So these are looking using surface waves and looking at the directions and polarizations of surface waves that travel fast and doing a seismic tomography model of that. And what people see, this is one particular model, but in lots of different models for the Australian continent, when you're at the base of the plate, so this is 200 and below, all the little black bars you can see are kind of mostly aligned kind of north-south, and they're quite similar to that absolute plate motion of Australia heading northwards, heading to collide with Asia. When you're shallower though, at like 100 kilometers, and you're very much within the lithosphere, the orientations here are more east-west. They're kind of different orientations. They don't look like the absolute plate motion. And people think this is a representation of some of the fossil anisotropy that's frozen in to the lithosphere. And this is a cartoon from another paper, just indicating that at the base of the Australian plate, from surface waves, there seems to be evidence of strong anisotropy at the base of the plate. So that's shear on the mantle. Another, and probably one of the most direct and common ways of looking at seismic anisotropy is to study something called shear wave splitting, which is what I've done a lot of in my career. And how this works is when you have an incoming shear wave in black encounters a region of anisotropy, like this box, it becomes polarized into two directions, fast and slow, so in blue and red. And we can measure seismically the orientation of the fast and measure the delay time between the fast and the slow, which gives us an indication of the strength of anisotropy and or the path length through the amount of anisotropy. So it's a bit like optical birefringence in mineralogy, if you're more familiar with that. Often to do shear wave splitting, we use core refracted phases like SKS or PKS. So these are, if you're not a seismologist, I'll explain what the SKS means. So these are, we have an earthquake over here. The wave travels as an S wave or a P wave down from the source to the core mantle boundary. It travels through the outer core as a P wave because the outer core is liquid, and we give that the symbol K. And then it emerges from the outer core and travels up towards a seismic station as an S wave. So these are really useful because when it converts from a P wave into an S wave, it removes any anisotropy in the mantle beneath the source, and it polarizes the shear wave as it's emerging from the core mantle boundary into a known orientation. So people have done this in the past, 15 or more years ago for Australia. So there's a couple of papers by Maggie Heinz working with Brian Kennett, who a few people who have been around for a while might know. And they looked at, this is showing Skippy and Tasmal stations, results of shear wave splitting. And I think you can see quite clearly from this picture that we do not see coherent fast directions, these bars aligned with the absolute plate motion. So I refer to this as the Australian shear wave splitting conundrum, in that we know the Australian continent is a really fast moving plate. We know it's exerting shear on the asthenosphere below. We can see that in the surface waves and the azimuthal anisotropy, but for some reason, it's not showing up in the shear wave splitting. So we decided to take a bit of a closer look at this. And a couple of years ago, I had an honours student, Claire Flashman, that many of you may know or remember. And she looked at SKS and PKS splitting for the BILBY array. So this was a transect of broadband seismic stations that were deployed in 2008, 2011, that crossed the Australian continent from north to south. It's like a 1,000-kilometre long transect, and it crossed through many different geological provinces. And what I'm showing on the left here in red and magenta are the station averaged fast directions that we retrieved in this study. And what you'll see is we're actually quite surprised to see that there's a really actually quite a strong consistency, this sort of east-west alignment of those the red bars. But as you go northwards and the orientation then of the geological provinces changes. So up here, we're in the Tennant Creek Davenport inlier. You see that the orientation of the bars and the fast direction, sorry, I can't actually move that thing, but the orientation of the bars then rotates to be more northwest, southeast, aligned with that inlier. And if we look in the middle panel, we've got the same station average results on top of the gravity anomalies. And in Central Australia here, in red and blue, you can see that we have these really strong east-west aligned gravity anomalies, which are from these deformation belts. And they actually represent offsets in the Moho of 10 kilometers or more that have been well studied and well known. So they represent significant deformation of the crust. And we can see that the signature of the anisotropy seems to align really well with the orientation of these gravity anomalies. And some of these, picture on the right is just a figure from an older paper also showing these gravity trends. So it certainly doesn't look like the absolute plate motion, but it's starting to look a lot like the geophysical character of the crust. We can look in more detail at this sort of this pattern with latitude. So on the left here is a figure from south to north along the x-axis. The top panel is the fast direction, and the bottom panel is the delay time for each of the station average splitting results. And we see that there's sort of a similarity in the results up to about 22 degrees south, which is about here. And then we see a sudden change where there's more variability and a difference, a switch in that orientation of the fast direction. In this figure, we're comparing the shear wave splitting results with a profile of the azimuthal anisotropy from the surface waves beneath the same profile as the BILBY stations. So this is a bit of a different way of looking at it. So I'll explain a bit more. So we're looking at a profile. We've got depth on the y-axis and latitude on the x-axis. I'm then taking azimuthal anisotropy model, which is derived from surface waves from Dubai 2016, which is updated. And each of the circles is kind of a grade point in that model and representing the value at that particular point. The size of the circle represents the strength of the anisotropy. So a bigger circle is stronger anisotropy. And the color of the circle represents in that model the fast direction of the anisotropy according to the color scale on the right. And I've indicated here what the equivalent color for the absolute plate motion would be. So it's kind of this brownish, maroon to brown color. So you can see here between 150 and 250 kilometers depth, we have really strong anisotropy is imaged from the surface waves, and it's very similar color, similar orientation to the absolute plate motion. And the gray band in the back is this sort of expected lithosphere, asthenosphere transition. So it's really at the bottom of the lithosphere, at the bottom of the plate. What's interesting is using the same color scale at the top, I'm plotting the BILBY stations and the results of the shear wave splitting. So the color is the fast direction, again, according to the same scale. And we see that consistency up to about 22 degrees south. All the stations are kind of a sort of pale, sort of beige color. And then we have a sudden transition to when the stations then become a more blue to kind of purple color. Now, if you just look just beneath that at the shallow, around 50 kilometers depth in the azimuthal anisotropy, you also see quite similarity in those colors, or similarity in those fast directions. So we go from having sort of pale colors into beige, browns, maroons, into blues. So it's quite similar to the pattern from the BILBY stations, but from the surface waves and tomography, they tend to smooth out this sort of signature laterally. So we get a very smooth transition. But with the shear wave splitting and using the receiver-based technique, you get a good result beneath each particular station, beneath each particular instrument. So you get like a point-based measurement. And what we can see using that is we can then detect this change seems to be more sharp than what's seen in the surface wave azimuthal anisotropy. And it seems to mostly reflect the shallower depth. So the take-home messages from this is that what we see from the shear wave splitting shows a really strong resemblance to the surface geology. And it appears to reflect, have the same pattern as what we know about past deformation of the lithosphere and the crust in this region. And it means that past tectonic events, those that I talked about, the gravity anomalies, they've created offsets in the Moho of 10 kilometers or more. That's huge amounts of deformation. To be able to do that must have also impacted not just the crust, but also the lithosphere. And potentially we can see it in the seismic anisotropy in the shear wave splitting. So another way to look or analyze seismic anisotropy that is perhaps a bit less, well, a lot less common, is to look at something called quasi-Love waves. And these are scattering of surface waves, in particular, scattering of love wave energy. So love waves are horizontally polarized surface waves into really wave motion, which is the retrograde elliptical type motion of the surface waves. So when you have a shallow earthquake, it generates strong surface waves. You have a love wave generated in green, and when it encounters a gradient in seismic anisotropy, some of that energy is converted into really wave motion. So this is a really, if we can observe that, this is a really cool way to be able to detect lateral gradients in seismic anisotropy in the upper mantle. So in this cartoon here, I have on the left, there's a block with a certain kind of fabric that's kind of aligned like this. And then on the right, we've got another block of material where the fabric is kind of aligned like this. So where we have a change in the fabric, the orientation of the anisotropy, or a change in the strength of anisotropy, we can generate this love to really scattering, or the quasi-Love waves. So on a seismogram, what this looks like. So on a typical seismogram, you will see the fundamental love wave in green that is polarized onto the transverse component. So that is the component in the horizontal plane, which is perpendicular to the source receiver ray path. In blue here, we have the fundamental Rayleigh wave, and here I'm showing the vertical component, but you also see it on the radial component, the horizontal pointing back towards the source. Because love waves travel faster than Rayleigh waves, so love's faster and Rayleigh's slower, when you have this quasi-Love wave generated, it's mostly traveled as a love wave, so it's faster, arrives before the Rayleigh wave, but it's slower than the fundamental love wave because it spent a bit of time traveling as the slower Rayleigh wave. It does, however, have the same shape as a love wave. It arrives before the fundamental Rayleigh, so we can easily detect it on the seismogram. And essentially, we cross-correlate these two seismograms and determine the delay time between the fundamental love and the quasi-Love wave arrival. In this equation, we can then use the difference in time between the Rayleigh and the love, this delay time, and we know the epicentral distance between the source and receiver, and we can estimate then the distance delta x from the receiver towards the point of scattering, or towards the location of that gradient in seismic anisotropy. Once we have that distance delta x, we can then back project along the great circle path to determine or estimate a location of that scatterer, or location of the boundary in seismic anisotropy. So people have applied this to several different tectonic settings and made some really interesting observations. I've got some examples here from regions of continental collision, seafloor spreading, subduction, and for the East Coast passive continental margin, which will become relevant later for Australia. In these previous studies, people were mainly targeting a particular plate boundary or a particular region where they expected to see gradients in seismic anisotropy. They expected these things to exist, and lo and behold, they did make observations and they did find them. I took a slightly different approach and used the Australian National Network and basically searched earthquakes from all around the world that kind of went out in all different directions and basically let the data tell me, where do you actually find, if you can search anywhere, where do you actually find these scatters or find these gradients in seismic anisotropy? So in blue here are all the ray paths on which I detected a Quasi-Love wave for this scattering. And that was about a fifth of the seismograms that I looked at that I could make a really good detection or observation. And you can see that they're quite widespread. When you plot then on a map the location of all these scattering points, you can see that they're quite widespread over the Australasian region. The circle represents scattering point, potential source of a gradient in anisotropy. The size of the circle is scaled by the amplitude of that Quasi-Love wave. Larger circles, we can be pretty confident about that we're seeing a strong gradient, but the amplitude is dependent not just on the strength of the gradient, but also on the geometry between the ray path and the geometry of the anisotropy. So just because the circle is small or even non-existent doesn't mean that there's not a strong gradient present. But really we're looking, we can trust observations, but a lack of them doesn't mean that there isn't a gradient. So I found mid-observations 275 new scatterers. They're quite widespread, but you can actually see some interesting geographical patterns. So about a third of the scattering points coincide with the continental margin. So that's outlined by the turquoise line. And when I say coincide, I mean that they're within 100 kilometers of that boundary. And I've highlighted, colored them in turquoise in the same color. That is the boundary between oceanic and continental crust. And then in yellow, I've done the same thing for crustal boundaries, the major geological provinces within Australia. And again, just less than a third of the points coincide with major geological provinces. There's known geological or crustal boundaries in Australia. If we look slightly different here, a lot of those, the internal crustal boundaries, here I'm plotting just in colors, the Precambrian oldest crustal components of Australia. And we see that there's a lot of scatterers in kind of northern and central Australia, particularly within this central deformation belt. And there's not that many actually within the interior of the cratons, but there are a few that kind of pop up around the outside. If we look at then compare with the free air gravity, and again at the gravity anomalies, and I've just highlighted here, we get quite a few scatterers that pop up on the edges of these really strong gravity anomalies, these east-west trending anomalies that I've mentioned before. And there's also a couple that pop up on the Darling Fault, again, where there's another really prominent gravity anomaly in Western Australia. So that's really interesting, but it came up in the reviews when I was submitting this work. Is it actually statistically significant? If you took the same study area and just randomly distributed a bunch of points, would you also come up with the same correlation? And the short answer is yes, it is statistically significant. There are more scatterers located closer to these features than you would expect if they were random. So I'll explain a bit more about these figures here. So on the left, we're plotting a cumulative distribution function, or CDF, of the percentage of scatterers that fall within a given distance from the particular feature. So in this case, from the ocean-continent boundary. In turquoise or blue is that distribution of observations or of the scatterers related to that boundary. In gray, there are 100 different gray lines or different CDFs, and these are 100 different distributions of the same number of points, but distributed randomly, what you would then expect that CDF to look like. The thin black line is the mean or the average of those 100 random distributions, and the thin dotted black line is one standard deviation either side. So you can see that for our observations in blue, the blue line is higher than those random distributions at short distances, which means that there's more scatterers closer to the ocean-continent boundary than you see in the random distributions. You can do the appropriate statistical test, which in this case is the two-sample Kolmogorov-Smirnov or KAS test, and you get a value of 0.04 or 4%. And if that value, typically the critical value we take as our significance level is 5%. If you're below that level, it means you can reject the null hypothesis that these two things are from the same distribution, essentially saying that our observations do not look like the same as the random distribution, randomly distributed points. So yes, ocean-continent boundary is statistically significant. And when we do the same thing, then for the Australian geological provinces, now in yellow, the significance is even better. So 100% of the scatterers fall within 150 kilometers from a geological boundary. And that's, if they were the random distribution, you'd expect it to be double that, about 300 kilometers. So whilst in the map shown here of different zones of distance from the boundaries, there are a lot of boundaries, and you are likely to hit a crustal boundary. But where we have the larger provinces, where the distances are greater, we don't see any scatterers, or very few scatterers, in the interior of the provinces. So we're seeing that we have more scatterers located close to the boundaries, all of them within 150 kilometers. And the significance there is really good. We're down to 0.09%. So it's very, very unlikely that this would have been generated by random. So the key points so far, we've observed widespread presence of lateral anisotropic gradients capable of generating these Quasi-Love waves. The locations seem closely linked to past plate boundaries or past suture zones within the continent. And it implies that such boundaries are preserved both at depth into the mantle and also over time. So many of these provinces are several hundred million years, if not billions of years old. We also know that the frequency that we've been making these observations at, about 100 seconds with the surface waves, that they have a peak sensitivity in the upper mantle between 100 and 200 kilometers depth. So that's much deeper than the crust. The main region of sensitivity is very much in the upper mantle. We're not looking at differences in the crust, but we are seeing a similarity between these observations and crustal or surface features. So at this such depths, 100, 150, 200 kilometers depth, the question then becomes, is this a signal from the lithosphere or from the asthenosphere? And the answer is it really depends where you are. Here at the bottom, we've got a cross section, again through seismic tomography model from Shear and Lebedev at 150 kilometers depth. So this is the sort of peak region we're sensitive to. The blue colors represent the lithosphere. The warmer brownish colors would represent the asthenosphere. So you can see that in all the scatterers in central and Western Australia, a lot of those were very much in the middle of the lithosphere. But when we're out east or Eastern Australia, we're most likely that scattering is occurring from the asthenosphere. And this is a cross section here through the same tomography model. You can see there, this would be the thick cratonic lithosphere. So I think that these scatterers within the lithosphere are picking up differences in the fossil anisotropy that's frozen in to the Australian lithosphere. It's heterogeneity in that anisotropy of the lithosphere. When you're at the western edge of the continent, or also a lot of these scatterers on the southern edge of the continent, perhaps that's caused where you're going from a transition from fossil anisotropy in the lithosphere to active flow in the asthenosphere. So you'd have a difference in the deformation and a difference in the anisotropy. For the east coast of Australia, when we're in the asthenosphere though, and on the west coast of Zealandia, where we also have a lot of scatterers, it becomes much more difficult to explain these as to what would be causing us to have scattering in the asthenosphere at such depths. I'll also point out here, there are observations along present day plate boundaries. So this is the New Hebrides subduction zone. So one idea I've kind of been thinking about is the models I'm showing tomography before. Those are global models. They're kind of a sort of blurred picture of the lithosphere and asthenosphere. But where we've had more dense deployments, such as Southeast Australia with the wombat arrays, being able to make much more detailed pictures of what the lithosphere-asthenosphere boundary looks like, and be able to create models of topography on that lithosphere-asthenosphere boundary. And up here is taking that LAB topography and calculating the mantle flow, which I believe was made by Rodri. Yes, which is in this paper. And what I'm sort of intrigued by is in gray would be the topography of that lithosphere. And then you move that lithosphere over the surface, looking at the mantle flow that's generated below. And even when you have variations in the topography, which are shallower than this depth that we're most sensitive to, 100 to 200 kilometers, highlighted in these dashed lines, you can still get deviations to the mantle flow, potentially deviations to the seismic anisotropy developing at such depths. And where you have steps in the lithosphere, you can generate edge-driven convection, shear-driven upwelling, and things like that, which very much can create localized convective cells. So putting that together, we've got two cross sections. This is west to east across Australia and Zealandia, and south to north. We think we've got evidence for fossil anisotropy within the cratonic lithosphere, and potentially we see a difference between that and active flow in the asthenosphere. Potentially where we've got a step, we've got some edge-driven or disruptions to the mantle flow field at the continental margins. But on either side of the Tasman Sea, the lithosphere is much shallower, but potentially there's deviations or there's a difference in how continental versus oceanic lithosphere couples to the underlying asthenosphere that's creating localized diversions in the mantle flow beneath these rifted margins. So take home messages there. The lithosphere has significant fossilized anisotropy. It seems to preserve a rich and ancient tectonic history that reflects the surface geology. I think we're seeing a disruption to the upper mantle flow field beneath the continental margins, which hasn't really been seen kind of in seismic observations before. It's quite difficult. All our seismometers are mostly on land. We have very few seismometers in the continental margins in the oceans. So it's difficult to make such observations, and maybe we've detected something new there. And I think these gradients in anisotropy potentially in the future can be a predictive tool to help constrain major tectonic boundaries in the continents at depths, particularly those that might be hidden beneath sediment cover and those which have deep mantle connections that might hold the potential for mineralization. So I think I'll just leave it there and then we'll have time for some questions. Thank you.
Are there any questions from group? And for folks online, feel free to type in your questions. On the back and then we'll do.
So it's kind of a very general question, really really understand these things, but how much anisotropy are you actually looking at? So in terms of the alignment of your olivine crystal, if you were just randomly oriented, how much would you need to rotate into a common direction to get the amplitude that you measure it? Almost completely perfectly aligned, or is it still just almost random with the tiny bias?
Yeah, no, it's not perfectly. It's a preferred orientation, not perfect orientation. So observations suggest, so the individual olivine crystals have an anisotropy of 16%, so 16% in the difference in the velocities of direction. But when in the mantle, when you deform it and create a preferred orientation, that's reduced to about 4%. Because as you said, it's not perfectly aligned. There's still some random orientations in there as well.
So do you have a feeling of what that actually means in terms of, like I said, starting with just a random orientation, how much you need to rotate the crystals approximately to get those kind of anisotropy? I mean, is it like 1 to 3, or is it that much more that that actually have to have a preferred
like the angle? How much? Well, that's more in terms of how it's working in the mantle. That's more a question of if you start with it random, you need to have a certain amount of strain or over a certain amount of time in order to cause enough rotation.
But what's the rotation? Is what I'm getting at. How big is that rotation?
I don't know what you mean by how big is they rotate. So they rotate so that they're aligned in the shear plane with the direction of shear. But it can be, there's not like a magic number, I can tell you. They can be anything, and then once enough kind of rotate into that given direction.
So that's kind of what I'm getting at. How big is that rotation you need in order to be able to measure it? So if, you know, on average, if you went to random, and on average you shifted everything kind of less than a degree towards the preferred direction, is that going to be enough?
No.
Or are you talking about a bigger rotation? So,
yeah, you're talking about a bigger rotation.
okay.
But I don't know, there's not like no, in terms of what I think you're asking, there's not like a magic number, I can tell you. Yeah. Okay.
So I love the results in the sense that there's so many dynamical questions that we need to answer that we can't answer at present. So that's very exciting. But one of the things I think that would be nice to help with that understanding would be to see how these observations differ in different continents.
Yeah.
So for example, Australia, it may be simple, demonstrates presently probably accepted, but it's very complex in the lithospheric structure. So potentially by looking at North America or something, we could see, do these features map to the continental ocean boundary, or something else. So I guess my question is, having looked elsewhere to see if there's a correlation between the continental ocean boundary and in other parts of the world, or is that just Australia?
No, but that's what I want to do.
Okay.
That's what
That would be awesome.
yeah.
I mean, it's awesome anyway.
Yeah, so you know this, I'm hiring so in the process of hiring a postdoc, and that's one of the things that I'd actually really like them to look at. Yeah, so we've seen this for Australia. There's similar observations for North America, but is this actually a global feature, or is this very specific to Australia and Zealandia? I don't know the answer yet, but I'm very intrigued by it.
Do you have a hunch?
Well, I hope it is. If it's a global feature and a global observation, then that'll be amazing. Yeah, because that'll be something that people haven't realized or seen before. Anthony?
A great talk, Caroline. In the previous slide to this one,
Yeah.
you had that vertical cross section, maybe one more. Yeah.
Yeah.
So there, your sensitivity range is kind of 100 to 200 K depth.
Yeah.
And that's kind of particularly underneath where it says plate motion. That's almost the range where you have a complete 180-degree flip of the flow direction.
Yeah.
Right, so just below that 200K line, you're completely changing the flow direction. So I just wonder how then that complicated if your sensitivity bleeds across that 200K boundary.
Right. So this is where I get to explain Rodri's model.
Don't touch the flow direction.
So this is, correct me if I'm wrong. So this model is like a box, right? So when you're having, correct me if I'm wrong, so if you're moving this on the top, you have shear at the top. If you're moving the flow in that way, you then create some kind of return flow. So I think that's partially in there, what's kind of creating the kind of flip. In the Earth, I personally wouldn't expect it that you'd have that flip in the direction with depth. More, I think you'd have a gradual over the upper mantle, you'd have strong shear, and that kind of would decay down with depth. So yeah, once you're deeper than that though, so I didn't get into detail, but seismic anisotropy is only generated by dislocation creep, not diffusion creep, and we expect that to start to come in at sort of deeper depths. So it's really the asthenosphere, so at those kind of depths that you really generate the anisotropy. But the mantle is flowing potentially in different directions, but the mechanism is different. Yeah. Oh.
Sean, Song, and you.
I have a tiny question about the observation.
Yeah.
So we can observe Quasi-Love.
Yeah.
And we also really
Yes, I haven't looked for it, but yes. There is, I know of at least one paper that has made observations of quasi-Rayleigh waves, but they're much more difficult to study because they arrive, so you would see those on the transverse component and they would arrive after the Love wave.
Yeah.
So it's harder to see something which is arriving after. It's easier to see the Quasi-Love wave because it arrives before. And as you know, it's easier to see the first thing that arrives, not a second thing that arrives.
Oh, thank you. I just remember some slides giving you so that you want to study the growing order of these prefer orientation for some station in skipping like so one of the early slides.
Yeah.
So the picture with observation hospital.
Yeah.
Yeah.
Oh, hold on. It'll take me a while to get.
Some orientations along these.
This one?
Yes. So do you have any insight in why they didn't observe them and you can observe?
Yeah. So there's more. So these are stations, Tasman and Skippy, temporary stations. They weren't out for very long. I think they only looked at SKS, not the PKS. And I think with these, it sort of depends. I think I found that I had to be very strict on the quality of the measurements. So I really had to be, for these temporary stations, you might only get a few measurements, and you have to be very strict on what you're very confident about and keep those ones. So I find it's better to be stricter and have a less number of measurements, but keep the ones you're most confident about, versus when you if I was working in other places, I could accept a broader range of measurements, but then the picture tends to be a bit more complicated. So I haven't looked myself at these particular stations, but I wonder if that might be part of it. They're also from much older deployments, so deployments from the 1990s. I think there's signal hidden within this, and it's something I'm working on at the moment, is actually for Southern Australia to try to map out more the lateral variations. But yeah.
The last question.
Can you go back to that slide that Anthony pointed to?
Yeah.
So,
I love that all the questions are the slide with Rodri's model.
so is that bottom one on the right? Is that from that paper?
Yeah.
Okay.
Yeah.
Yeah. That's one question. The other question was, so like if you've got high temperature melting sort of along the lithospheric boundary, potentially, adding residual mantle on or recrystallizing mantle, how would that sort of affect, or have you sort of considered the complications of that, of course?
Yeah, no, I haven't. But
because I guess if that happened, it would completely wipe away fabrics that have been previously.
yeah, but you would still, so you're not. Yeah, so you're not going to completely. We're talking, when I'm making observations, we're looking kind of averaging properties over like 100 kilometers extent, right? So you're not going to have 100 kilometers of pure melt, right? But what people sometimes have sort of proposed is, if you are getting melting and you create layering in that melting, that can also generate when you then look with seismic waves, that can also generate anisotropy from something called then a shape preferred orientation. So basically having different layers of material. That's not something that I think that I'm seeing, or I think would be prevalent here. But certainly, yeah, I think patterns of upwelling and melting are things that I tend to ignore. But I think are very interesting signals of the dynamics of the upper mantle as well.
Is that exciting? Thank you, and we look forward for global Quasi-Love. With that, there's social hour hosted by the students below. Please join and then have a good long weekend.
Thanks everyone.